Hi, this is Rahman Momeni from GMV NSL. Water is a key element for food and agricultural production with a crucial role in food security. On average, the agricultural sector accounts for 70% of the fresh water of the world. Drought as a form of natural hazard is a threat to our water resources and food security. Drought in general terms occur when a precipitation rate becomes below the average levels due to lower either rain or snow. This study, as a part of H 2020 project, we focus on agricultural drought with not only considering the precipitation factor but also soil moisture levels and vegetation conditions. This study aims to analyze and reconstruct the history of drought in Somalia. According to FAO, the percentage of the planet affected by drought has more than doubled in the last 4 decades, with the highest impact being in the agricultural sector. For example, according to the World Bank, drought in 2016 had left 40% of Somalians' population food insecure. This resulted in acute hunger of 6.3 million of Somalians the next following year. We choose Somalia as a study case since this study affected by drought over the last 10 years, which resulted in hunger for nearly 50% of the country. You can see a sample of a study area we chose here, which is north of Mogadishu in Somalia with more than 1.2 million hectares. This is the flowchart of develop methodology, which is derived by combining 3 main drought indicators. From the right is SPEI, which stands for Standardized Precipitation Evapotranspiration Index. It considers both precipitation and potential evapotranspiration. We analyzed SPEI from January 1950 to December 2010. The next element is Soil Moisture Anomaly Indicators, which is based on ESA Climate Change Initiative Soil Moisture. We analyze soil moisture index temporal coverage from 1978 to present, which is 2020. The last and third factor is Normalized Difference Vegetation Index Anomaly, which is computed as a deviation of the biophysical variables NDVI extracted from the Sentinel-2 datasets. It's analyzed from December 2015 to December 2018. Our agricultural drought indicator is a correspond to the different stage of the cause-effect relationship for agricultural drought, whereby a shortage of precipitation leads to soil moisture deficit, which in return result in reduction of vegetation productivity. This indicator is computed by combining anomalies of precipitation, soil moisture, and vegetations, using a classification scheme which you can see at the bottom in the blue box, consisting of 3 drought levels: watch as a yellow, warning as orange, and alert as a red color. Watch aims to detect early stage of drought, while alert monitor more advanced stage of drought. In this slide, I would like to show you some results, which here you can see 2 periods with severe drought represented as an alert category, if you remember from last slide, as also you can see in the right side of each of this image. There are 4 categories: green, yellow, orange, and red. So green means there is no drought. As I explained, the red means alert, orange means warning, and yellow means watch level. So as you can see, in July and August 2017 there was a drought in the study area, and by the time it's progressed, the droughts become even more severe. At the bottom you can see the trends of the changing of these 3 indicators during the time. Each pixel, each point here basically represent the average of all pixel, all of the 1.2 million hectares. Here in the last slide, I would like to quickly go through the advantage and disadvantage of develop method and the next steps of the improvements. So compared to other drought indicators which relies on only meteorological or hydrological data or remote sensing imagery data, or a combined drought indicators integrate those 3 elements, which This integration can help to reduce the alarms, false alarms. In addition, our method can provide a drought map for every 3 days with 10-meter resolution and global coverage. One of the limitations of the developed method is not producing the accurate result in snow because of the similar NDVI more than 0.5 for snow coverage. But since this is Somalia is not the climate with the snow, this is not any problem for our methods. The next steps for improvements are enhancing cloud removal algorithm, having similar temporal consistency between NDVI and soil moisture index anomaly for every 10 days, test to see if having this SPEI for every 3 months instead of 1 month going to improve the performance of the algorithm. Finally, excluding the NDVI values exceeding the 90% of the standard deviation. Thank you.